Welcome, everyone. Today we'll be presenting our project on using artificial intelligence to assist in dementia diagnosis. Our goal is to explore how artificial intelligence and interactive memory games can support patients and caregivers. To make this project clear and organized, we split it into four parts. First, we'll explain the process of dementia and the challenges involved. Second, we'll discuss the psychological memory models that guide our game design. Third, we'll show how AI assists in scoring, predicting, and personalizing the game experience. And finally, we'll explore the potential impact of this technology. Before we begin, I'd like to introduce our team. My name is Jiapeng Zhu, and I served as a lead developer focusing on machine learning and data modeling. I am from Rancho Cucamonga High School in California. Next is Claire Zhou. She focused on game design and user experience, and she is from Cambridge, Rindge, and Latin School in Massachusetts. Lawrence Tran worked as our system engineer. He handled feature extraction, analytics, and technical testing. He is also from Rancho Cucamonga High School. And finally, Ruoying Tang focused on research in cognitive science and memory theory. She attends Los Osos High School in California. Together, our diverse backgrounds allowed us to work together and build this project.
So, what is dementia? Dementia is an illness where there is a progressive decline in memory and thinking. It affects millions of people worldwide and is most common in older adults. So, early detection matters since it can let patients access to treatment earlier and it slows down their worsening of symptoms. So, with current tests, for example, PET scans and spinal fluid analysis, the problem is that they're expensive, invasive, and inconvenient. We took note from three memory models, which include the Atkinson-Shiffrin multi-store model, which describes it from sensory to short-term to long-term, and then there's the Blatty's working memory model, which describes working memory as a dynamic memory system responsible for temporarily storing and manipulating information. And last but not least, there's the Global Deterioration Scale, which is the GDS. It labels dementia from stages 1 to 7 to describe the possible mental stages someone can be in. So, I'll provide an overview of several key memory systems that we concluded with. These are 5 memory systems. So, firstly, we have working memory, which is a dynamic system responsible for the temporary storage and manipulation of information. It supports a high order process such as reasoning, comprehension, and problem solving. Second, we have procedural memory. It constitutes as a component of long-term memory. It involves the acquisition and the retention of skills through repeated practice, such as riding a bicycle, typing, or playing an instrument. Third, episodic memory. It enables individuals to recall personal experiences. It allows access to past events, complete with contextual details such as time, place, and associated emotions. Fourth, we have semantic memory. It differs from episodic memory that stores in general knowledge, concepts, and facts about the world. It includes like science principles, historic data, or the meaning of words. And finally, we have sensory memory, which represents the initial stage of information processing. It involves the brief retention of sensory input, such as visual impressions, auditory signals, or what you see, what you hear, before the information either fades or progresses into short-term memory. So together, these systems illustrate the complexity of human memory and its essential role in learning, adaptation, and daily functioning. And so we based off our model based on these 5 types of memory models. So the human memory can be described in 3 main stages. First is the sensory memory, lasting from only 1 to 2 seconds, which briefly retains information from the senses. Secondly, we have the short-term memory and then the long-term memory. So the short-term memory lasts about from 1 to 2 minutes. Within it, working memory actively processes and manipulates information for tasks such as reasoning and problem solving. And lastly, as I mentioned, there is long-term memory, which can last a lifetime. It includes implicit memory, such as procedural memory for skills, explicit memory, which requires conscious recall. And so explicit memory further divides into episodic for personal life events and semantic for facts and knowledge. So together these systems explain how humans take in, process, and store information. So this model is what we illustrated to show how different types of memory can be strengthened through the interactive games that we created. So for sensory memory, players are asked to recall information after a brief exposure, such as colors, patterns, sounds, or materials. Activities may include multiple choice recognition or storytelling tasks. And so in working memories, players practice holding and manipulating information. Examples include repeating number sequences, arranging steps of a routine in the correct order, or engaging in short conversations with robots. For procedural memory, games involve real time skill tasks. Players might record actions such as tying shoes, followed by self assignments and AI feedback to improve performance. And episodic memory is supported through activities like arranging life events on a timeline, flipping cards to match memories with images, or identifying personal moments from photos. Finally, we have semantic memory, which is strengthened through the knowledge based tasks. These include trivia style categorization, filling in blanks, or answering true or false questions based on personal education input. Together, these activities form a comprehensive game engine that trains multiple aspects of human memory engaging and meaningful ways.
Hi, my name is Tran, and I'll be discussing the four formulas that make up the scoring system. Players receive a base score of 3 per correct answer and 0 points if incorrect, denoted as Sij. I represents the different memory type subgames with an index between 0 through 4, and J represents the question number in that subgame with an index between 0 and n-1, where n is the total questions in I. Sij will then be adjusted according to the time spent and hints used per question. Let Tij and Hij be the time and hint adjustments for Sij respectively. The formula is as shown. Each subgame score, denoted by SGI, is the sum of all adjusted scores in I. The total game score, ST, is the summation of all weighted averages, WI, of each memory type subgame. For instance, research work indicates that dementia affects short-term memory more significantly, so its weight is higher. However, weight assignments will be included in our future work. Say a player is given n equals 10 questions, then the maximum possible total game score, after adjustments, is 250. This does not necessarily mean that each question is worth exactly 25 points. In addition to the total score, the difficulty of the last correctly answered question will be attached to the subgame array. As an example, one player can have semantic memory with a score of 38 and reach a difficulty of medium. Assume the baseline time for answering a question is t0, and the player takes t time to answer that question. For faster answers where t is less than t0, the player may receive bonus points. However, for slower answers where t is greater than t0, penalty points may be deducted from the player's score. The time adjustment, ti, for question j of subgame I is calculated as follows. Similarly, the number of hints used can also affect the player's score, with function hij representing this. Like time adjustments, h0 is the baseline number of hints, and h is the hints actually used. If h is smaller than h0, then bonus points are added. However, exceeding the baseline number of hints will deduct points. Note that time and hint adjustment calculations are scaled to be between range -1 and 1, so that the maximum bonus or penalty is only 1 point. For example, given a baseline of 1 hint, a player who used 0 hints will receive a 0.25 bonus point, while a player who used 4 hints will deduct 0.75 points.
Let me go through my part of the project. We're building a game to help with memory recovery for Alzheimer's, and my focus was on the data, design, and some prediction model. First, let's look at this table. We collected user data like age, gender, ED level, that's education level, health status, and prior diagnosis. We also tested everyone on 5 key memory types. Working memory, this is like your mental scratchpad for holding information temporarily. Short-term memory, this is for recalling information from a short while ago. Procedural memory, your memory for skills and habits like how to ride a bike. Episodic memory, this is your autobiographical memory for recalling specific events in your life. Semantic memory, this is your memory for facts and general knowledge. For each of these, we have both a score like WM score and a difficulty level like WML level, easy, medium, and hard. By combining these scores with background info like age, gender, ED level, and health status, our model can make a much smarter prediction. The final prediction classifies user into 3 groups: no impairment, mid-moderate impairment, severe impairment. This classification is what allowed our game to recommend the right difficulty level rise for the start. Now we can trust this model. That's what this chart is for. We use a technique called scenario analysis to stress test our model. We intentionally add some random noise or errors into the data. It is what the R equal 0, 10, 20 represents. It's like testing how stable a boat is in slightly rough water. As you can see, even as we increase the randomness, our model's prediction bars remain relatively stable and accurate compared to the actual label. This proves that our model is robust. It won't break down or make wildly inaccurate prediction if it encounters slightly expected or messy user data, which makes it reliable for real-world use. The main game interface for the game we are going to develop, the home page, and how to play the game. What we hope is to provide players with different game assistance in 5 different memory directions, as mentioned earlier, allowing them to choose freely. The game interface and questions are designed to be concise, making it easier for users to use and operate. The questions are all in the form of multiple choice questions to help patients with Alzheimer's disease make a better choice. So in short, we use the data to build a model that reliably predicts a user memory level and to design how to play the game. This will help the game automatically adjust its difficult for each person. That's my part. Thanks.
Hello, everyone. My name is Jiapeng Zhu, and I'll be wrapping up our presentation on dementia in our AI enhanced memory game. In this section, I'll talk about how we tested our model, what results we observed, and the impact that this project could have. So, starting off, for our approach, we used a random forest model because it's both accurate and reliable for classification tasks like this one. Before training the model, we pre processed the data carefully. For variables that had a natural order, like age and education level, we applied an ordinal encoder. For variables without an order, such as gender, we used a one hot encoder. Once the data was ready, we split it into training sets and a testing set, with 30% used for training and 70% used for testing. This setup helped us ensure that the model would perform well on new and unseen data. Now, looking at the results, there's 2 clear patterns that stood out. First, the accuracy of the random forest model improved as the data size increased from as few as 100 samples up to 1,000 samples. More data meant the model had more examples to learn from, which boosted its performance. Second, we found that accuracy was higher when there was less randomness in the data set. In other words, the cleaner and more structured the data was, the more reliable the prediction was. Taken together, these findings show that our model is promising and could be even more effective with larger and higher quality datasets. A very important aspect of our project is the entertainment factor. Traditional cognitive assessments can feel stressful, repetitive, or even intimidating for many people, especially older adults. By using a game based format, we make the experience more comfortable and engaging. When users enjoy the task, they are more likely to participate willingly and repeat the game regularly. This repeated play improves the quality of the cognitive data we collect. The interactive tasks also help motivate the user and reduces the pressure associated with formal testing environments. Overall, making the game enjoyable increases accessibility, encourages natural behavior, and helps us gather more reliable cognitive measurements. Now, I want to walk you through how our game works with actual people by showing three different sample scenarios. These are based on the sample cases we built into our model, and they help show how the game responds to different levels of memory ability. First, we have someone with a healthy mind. This person plays through all five sub-games and absolutely crushes it. They reach a hard level almost every time, they answer quickly, they barely use any hints, and their overall score is extremely high. The system looks at this and instantly recognizes, okay, this person is doing great, there's no sign of decline here. So it places them in stage A, meaning they have no cognitive impairment, which is exactly what we expect from someone with strong memory skills. Now, I want to talk about the second scenario, which is the most important one. Someone with mild or moderate decline. This person is still independent, living their normal life. They're not showing obvious symptoms that would send them to a doctor, but they're noticing little things, such as forgetting steps, losing their train of thought, or mixing up short instructions. And this shows up in the game. So when they play, they struggle in the working memory subgame. They take much longer on quick thinking tasks. They forget sequences easily, and they use more hints. But here's the interesting part. They still do well in long-term tasks like episodic memory and somatic memory. They remember life events, they know facts, and they can recall things from years ago. So their score ends up in the middle range, not terrible, but not great. And that's exactly where early dementia often hides. The game picks up on this very specific pattern: weak short-term memory plus strong long-term memory, which is one of the earliest warning signs of cognitive decline. Because of that, the system places them in stage B and tells them, hey, you should probably follow up with the doctor. This is huge because catching decline at this stage gives people the best chance to slow it down. Now, finally, we have scenario 3, which is someone with severe decline. So, this person struggles across basically the entire game. They may not recognize pictures, they forget instructions right away, and they get confused even with help. They can only handle the easy level, and even that is difficult. Their score ends up very low, which clearly tells the game they're in stage C. For this person, the system recommends immediate support or professional care because their memory decline is already very advanced. So these three scenarios show exactly how our game works with actual people. It recognizes strengths, it spots weaknesses, and it helps people get support early, long before serious decline takes over. Now, moving on to the impact of this project. The project is centered around being accessible, comfortable, and being able to provide early detection. Our game creates a safe, non-invasive way for people to monitor their cognitive health at home. Without needing expensive scans or specialist appointments, it makes early screening more affordable and available to a much wider population. The game also adapts its questions dynamically based on the player's performance, which allows for more personalized and more accurate tracking. Early detection plays a significant role in improving long-term outcomes for patients, and our tool supports continuous monitoring over time. Our hope is that this project can help bridge gaps in access and offer families a simple, comfortable method for keeping track of cognitive changes. Next, for future work, one of our main priorities is to run pilot studies with neurologists and psychologists to compare our game results with well-established cognitive tests, such as the Mini Mental State Examination (MMSE) and Montreal Cognitive Assessment (MoCA). This will help validate accuracy and ensure the tool holds up in a real clinical environment. We also plan to conduct long-term studies where users play the game regularly over longer periods of time. This will help us understand how well our tool can detect early decline before major symptoms appear. We want to continue refining the sensory and episodic memory task because these areas are often impacted earliest in dementia. Another key step is creating dashboards that visualize patient trends clearly. Finally, we hope to partner with senior centers, clinics, and research labs to expand deployment and gather larger datasets for improving the model. We would like to express our sincere gratitude to everyone who supported this project. But most importantly, we want to thank Professor Lang Yang from California State Polytechnic University Pomona for her invaluable guidance and support throughout the development of this project. Without her insight and support, this project would have been impossible. In conclusion, this project demonstrates how artificial intelligence and game design can work together to create a meaningful tool for healthcare. Our results are encouraging and the potential impact is substantial. Thank you guys for listening. Bye.